Let's say I have a linear transformation as a square matrix A here. It could be the case that multiply by A does not change the direction of my vector V here. So if I multiply this orange vector V to the matrix A, that's the same as just scaling my vector V. So here, this A is a matrix, this V is a vector, and then my lambda here is just a number. In this case, I'm gonna call this purple number an eigenvalue, and I'm gonna call this orange vector an eigenvector. So let's kind of see that in the example down here. Let's say my matrix A, this is going to be 2, -2, -1, and 3. If I multiply this matrix with a vector 2, 1, let's kind of see what happened here. So what I'm gonna get is my top number is gonna be 2 times 2 plus -2 times 1. So I have 4 minus 2, which is a 2. I'm gonna have -1 times 2 plus 3 times 1. So that's -2 plus 3, and that's a 1. Notice that I actually get the same vector out. So what that means is this vector, this orange vector 2, 1 that I'm looking at, this is an eigenvector for my matrix A. Now notice that this 2, 1, this is just the same as 1 times the vector 2, 1. So I can say that this number 1 here, this is an eigenvalue for my matrix A. Or I can say that this vector 2, 1 is an eigenvector corresponding to an eigenvalue 1 here. Let's try again with vector 6, 3. So if I multiply this guy to the matrix 2, -2, and then -1 and 3, I multiply this to the vector 6, 3. So what I'm gonna get is that my top number is gonna be 2 times 6 plus -2 times 3. So that's gonna be 12 minus 6, and that's gonna be a 6. And then I'm gonna have -1 times 6, which is -6, plus 3 times 3, which is 9. So I'm gonna have a 3 down here. So again, when I multiply 6, 3 to the matrix that I have, I get the same thing out. So this 6, 3 is indeed another eigenvector, and this 6, 3 is just the same as the vector 6, 3 itself times 1. So this number 1 is my eigenvalue. Notice though that this is the same value that we have from earlier, and in fact, the vector 6, 3 is just 3 times the vector 2, 1 that we have from earlier. So in a way, there are many eigenvectors that correspond to an eigenvalue. However, most of the time, they are gonna be just a scale of each other. Or we can say that eigenvectors of this matrix corresponding to the eigenvalue 1 are gonna be just vectors from the span of 2, 1. Now let's try again with vector 1 and -1 here. So my matrix is gonna be 2, -2, -1, 3. I'm going to multiply this matrix by vector 1, -1. And let's see what I'm gonna get. Well, I'm gonna have 2 times 1 plus -2 times -1. So I'm gonna have 2 plus 2, which is a 4. And then I'm gonna have -1 times 1 plus 3 times -1. So I'm gonna have -4. Notice that although I actually don't get the same vector back, but this vector for -4, I can simply just write that as 4 times 1 and -1. So indeed, this vector that I have, 1, -1, is going to be an eigenvector for my matrix here, and this number 4 is going to be my eigenvalue then. Now let's try again, but my vector this time is going to be -10 and 10. I'm going to have this matrix here multiply to the vector -10 and 10, and let's see what we get. So I'm going to have -20 minus another 20, so that's going to be -40. And then I'm going to have -1 times -10, which is a 10, plus 30, and that's going to be 40. Once again, I don't get the same vector, but what we have here is just 4 times the vector that I have from earlier. It's just going to be 4 times -10 and 10. So what that means is the vector that I have here, this is an eigenvector for my matrix A, and the number 4 that we have, this is an eigenvalue for the matrix A. Once again, notice that this is the same eigenvalue that we have from earlier, and the vector -10 and 10 It's just the same vector, but I just scale it by -10. So basically, anything in the span of 1 and -1 is going to be an eigenvector for the eigenvalue 4 here. So let's kind of see what this all means graphically as well. Here I have a linear transformation A to -2, -1, and 3 that we have from earlier. And this matrix would transform my blue vector into the green vector that we see here. So if I move my blue vector around, this is what the linear transformation does to my vector. However, notice that if my vector is 2, 1, then the green vector overlaps precisely with the blue vector, and this is because the blue vector is my eigenvector. And any scale of this vector is also going to be my eigenvector as well, and the same goes in the opposite direction too. Another eigenvector that we see from earlier is this vector 1 and -1 here. Notice that my green vector now is gonna be in the same direction, but we kind of scale it by 4 times, and that number 4 is the eigenvalue that we see from earlier as well.